Welcome to the lab module number 3, measuring the elastic modulus of materials by using acoustic wave speed measurements. In this lab, we will be using an oscilloscope coupled to an ultrasonic transducer in a pulsing receiving mode to measure the wave speed of the ultrasonic sound through the material of interest. Using the measured wave speed data, combined with measuring their density, we will calculate the elastic modulus of the materials. The elastic modulus, or Young's modulus, of a material is related to the stiffness of the bonding atoms in the solid. Different bonding types, such as covalent, metallic, ionic, hydrogen bonds, and van der Waals type bonds have different stiffnesses associated with them due to the difference in strength and bond lengths of the atoms involved. This bond stiffness then translates into the elastic stiffness or elastic modulus of the materials. Measurement of the elastic modulus can be obtained from the linear portion of a stress-strain curve derived from a tensile test of the material. The slope of the elastic region, the relationship between stress and strain in the elastic region, is referred to as the elastic modulus or elastic stiffness of the material. The challenge in measuring modulus from a tensile test is the difficulty in measuring strain accurately. We can measure stress very accurately. However, strain, which is the change in displacement divided by the initial length of the sample, is very difficult to measure because the displacements in the elastic region are very small and hence very difficult to measure accurately. And therefore, strain becomes a very difficult parameter to measure accurately and hence creates a large error in the slope of the elastic region and therefore large differences in the measured modulus of the materials. A more accurate technique to measure the modulus of a material relies on measuring the sound transmission through the material. Sound pulses are elastic stressors in the material, as shown on the left diagram. The ability of the material to transmit a sound pulse, or to dampen it, depends on the area of the curve underneath the elastic portion of the stress-strain curve, shown as the capital U in the diagram. This U represents the losses in the material. These losses can be a result of a number of different phenomena, but the primary contributor is the stiffness of the atomic bonding. Typically, sound transmits faster through higher elastic modulus materials due to the rigidity of the bonding. Higher density materials tend to result in lower sound velocities through the material. As a simple example of the difference in the frequency of the sound created by different materials, we will strike blocks of material of similar size of 3 different materials, lead, aluminum, and wood, and allow you to hear the sound of the impact between these materials and a steel hammer. The difference in sound is associated with the difference in material properties. The properties range from very high density and low modulus to moderate density and higher modulus to very low density in the wood and a moderate modulus. This is the sound of a ball-peen hammer striking a lead block. This is now the sound of a ball-peen hammer striking an aluminum block. Here is the sound of a ball-peen hammer striking a wood block. When the lead is impacted, it makes a rather dull thump sound. As you listen to the sound of a lead bar being hit by a small hammer, it has the lowest frequency of any of the sounds created. Based on these demonstrations of the sound of impacting different materials, one can see that it is possible to tune or tailor the sound made by the impact through the combination of choosing the appropriate density of the material, the choice of the elastic modulus, and the third component is the shape or geometry of the object that you're striking. These different features can be tuned to produce the sound, as demonstrated here, of a bronze bell. Compare the sound from the lead bar impact to the sound of a bell made of bronze. Bronze is a copper alloy that has a relatively high elastic modulus and a moderate density, the combination of which produces a very much higher frequency sound than the impact of the previous materials. In the latter half of the 17th century, Sir Isaac Newton published a famous work wherein he thought he correctly predicted the speed of sound through a medium, whether solid, liquid, or gas. His argument was that if he knew the density of the medium and the pressure acting on the sound wave, he believed he could ascertain the speed of sound by calculating the square root of the pressure divided by the medium's density. This approach was later modified by Pierre-Simon Laplace, and the combined work is referred to as the Newton-Laplace equation for wave speed. In the Newton-Laplace equation, the sound velocity v is equal to the square root of k, the bulk modulus, divided by the density of the material. In this lab, we are looking to ascertain the Young's modulus or elastic modulus E. So using the relationship between bulk modulus and elastic modulus, we can convert the Newton-Laplace equation, modifying it for the elastic modulus or Young's modulus. Now the sound velocity is equal to the square root of Young's modulus or the elastic modulus times 1 minus Poisson's ratio, all divided by the density rho times 1 plus Poisson's ratio times 1 minus 2 times Poisson's ratio. We will be using this latter equation. We will be measuring the sound velocity, and we will be measuring the density rho. We will use known values of Poisson's ratio, and from those values, we will calculate the value E, the elastic modulus, from the Newton-Laplace equation. In this lab, we will pass acoustic waves through a material of known thickness, and we will measure the time it takes for the acoustic wave to travel through the sample, reach the other side, and then reflect back to the transducer. In this way, the transducer acts as both a pulsar, sending the signal into the material, and a receiver collecting the signal that comes back. Each time a pulse is sent into the material, it will travel twice the thickness of the material, one thickness going in the forward direction and one thickness as it travels back towards the transducer. So the total thickness the wave will travel is twice the thickness of the material. If we look at the time difference between when the pulse is sent and the time it comes back, we can take twice the thickness divided by that travel time to calculate the sound speed. To calculate the sound velocity in the material, we use a pulse generator for generating the pulses that the transducer will send and receive, and we use an oscilloscope to measure when those pulses are transmitted and when they come back. An oscilloscope is a very high-speed signal sensing device with a capture rate into the hundreds of megahertz range. Using the oscilloscope to capture the waves allows us to determine the time delay between the pulse being sent and it being reflected back to determine the full transit time. We will be measuring the acoustic wave speeds for several different metals and several different polymer materials. For each material, we will measure the transit time for different thicknesses of the material. To do this, we have made a series of step-like samples in which each step is a different thickness, and that allows us to determine the accuracy of the measurement of the transit time. We will measure the transit time at each different thickness, and since the wave speed should be the same for the material irrespective of the sample thickness, we can use the measurements at different thicknesses and find the average transit time for all the different thickness steps and use those to determine the wave speed of each material. Each stepped sample has 5 different thickness steps. The protocol we will follow in this video is to use the name of the material and the number from 1 to 5, with 1 representing the thinnest step and 5 representing the thickest step. For example, copper number 1 would be the copper step sample and the thinnest step of the sequence, step 1. Copper number 3 would be the middle step, and copper number 5 will be the thickest step. We will use the same naming nomenclature throughout the lab, and the material followed by a number corresponding to the material and the step in the sequence. In the case of the polymer samples, due to the low wave speed and high attenuation of the pulses in these polymers, we will only be measuring the wave speed for the 3 thinnest steps, 1, 2, and 3. Recall that we also need to measure the density of the materials. There are several ways to measure density, but for the purpose of this lab, we're going to measure the density by using the simplest method, which is to measure the mass of a sample and calculate the volume through measurements of the dimensions of each sample. Recall that density is mass per unit volume. So for this, we've made samples of each material in a rather simple geometry, either rectangular prisms, as shown here for the polymer samples, or cylindrical rods that we've made for the metallic samples. As we go through the lab, we will be measuring the dimensions of each sample in this manner that will allow very simple calculations of the density. We will measure the length, width, and thickness of each of the rectangular prisms, from which we will calculate the volume of the polymer samples. Or we will be measuring the diameter and length of the cylindrical rods for the metal samples. Then we will weigh the samples in a simple balance, use the mass determined from the weighing process, and calculate the volume of the sample from the dimensional measurements of the samples, and we will calculate density from those values. We will do that and repeat it for each sample. And we repeat it for the metal samples in the cylindrical form as well. Now we outline the method to determine the density of each material. We will take each material and measure the dimensions of the rectangular prisms machined from each of the polymer materials to determine the volume of each sample. We're going to measure the length, width, and thickness of each rectangular prism. We'll measure them at two different ends and take the average value and use these three measurements, meaning 6 measurements in total, 2 for each side of the sample. We will average the 2 measurements from each side of the sample and use those to calculate the volume of the sample. Here we've made measurements of the length, width, and now thickness of the sample and recorded each of those numbers and used them to calculate the volume of the sample. Next, we take the sample block and put it on our balance and measure the mass of the sample. In this first example, the mass is 8.4 grams. At the end of this video, we have repeated this process for each of the other polymer samples. As you watch the video for each sample, record the dimensions measured and the weight of the samples to be incorporated into your spreadsheet to be used to calculate the modulus. In addition, keep track of the variations in the measurements to allow you to assess the potential errors in the calculations. We now take the Delrin step sample as an example of the measurement for the step sample thicknesses. We measure the thickness of each of the 5 steps. We're going to do this so that we know the distance the ultrasonic wave is going to travel, going from the front surface of the step to the back, and then back to the front where the transducer will pick up that signal again. The ultrasonic pulse will continue to reflect back and forth in the sample, so there will be multiple pulses picked up by the transducer. But they will be of decreasing intensity due to the attenuation of the wave amplitude associated with energy loss vibrating the atoms as the wave propagates. We will do this for the 6 polymer samples shown here, as well as each of the metal samples for the metal stepped samples that we have. We will demonstrate the measurement of 2 of the samples and then allow you to do the same measurement procedure for each of the other step samples, which are included at the end of the video for you to record all the data. Next, we will make dimensional measurements for the metal cylindrical samples, from which we will calculate the density of these materials, measuring the mass and the volume of each cylinder. The metal density samples are all right regular cylinders, and we'll start by showing you the measurement of the cylinder diameter, and then its length, and then the mass for each sample. We will use the copper cylinder as the first demonstration. Again, the sample is a right regular cylinder, so we measure the diameter of the cylinder. We measure at a few locations, and it's very close to 9.3 millimeters everywhere. Then we're going to measure the length of the cylinder, which is approximately 30 millimeters long. We can repeat the measurement a couple of different places, and you see that it's 30 millimeters within about 2/10 of a millimeter. So we have an approximately 30 millimeter long cylinder. From those two measurements of the diameter and the cylinder length, we can determine the volume of the cylinder. Next, we place the cylinder on the balance and measure its mass to be 19.13 grams. Now we can take the measured mass combined with the volume calculated from the measurements of the dimensions of the sample, and we can determine the density of the material. Now we will demonstrate the measurement of one of the stepped metal samples, measuring the individual step thicknesses. Again, this process is repeated for each of the other metal step samples included at the end of this video. Once again, we will demonstrate this for the copper step sample. The step sample contains 5 steps. We will begin by measuring the thickness of copper step 1, measured to be 1.4 millimeters on one edge, and when flipped over, measured on the other edge to be 1.5 millimeters. So it's approximately 1.5 millimeters in thickness for step number 1. And then this is repeated for each of the other 4 steps. Step 2 is roughly 3.3 millimeters. Step 3, the copper step number 3, is 5.3 millimeters. Copper step 4 is 7.3 millimeters, and copper step 5, the thickest step, has a thickness of 9.4 millimeters. Once again, this measurement process is repeated for the 3 other metal step samples included at the end of the video. Now we proceed to making the acoustic wave speed measurements. To do this, we must connect the ultrasonic transducer that will generate the acoustic pulses to the pulsar unit itself via a cable. The pulsar unit is designed to generate the pulse that will be sent through the sample, and the transducer will also receive that pulse back. This is the panametrics pulsing unit. Here we show you the end of the connector and the transducer. The transducer is a piezoelectric crystal, which when you apply an electrical bias across the crystal will change dimensions. By changing that bias at very high frequency, you can make the crystal oscillate in shape, extending and returning. Basically, turn the transducer into a high-frequency tapping instrument. We're using that high-frequency tapping, in this case at 500 Hertz, as a pulse frequency to cause the crystal to change length back and forth, creating essentially a high-speed hammer that's going to tap on the sample. That's how the acoustic pulses are created. We refer to them as acoustic pulses because the frequency of 500 Hertz lies in the range of frequency that a typical human is able to hear. The typical human can hear between about 100 Hertz and about 18,000 Hertz. The panametrics pulsing unit is configured to operate the transducer in both transmission and receiving mode. In other words, we're going to use it to generate the pulse, where we apply a voltage across the crystal to make it change its shape. And then we're going to allow the pulse, upon return to the transducer, to compress the transducer and convert the compressing of the transducer into an electrical pulse. To ensure that we get good coupling between the transducer and the sample surface, we use a very high viscosity coupling gel that eliminates the air gap between the transducer head and the sample surface. This allows the ultrasonic pulse to be more effectively transmitted through the sample. We place the transducer into the couplant and then press it firmly against the copper surface. Here, the back side of the copper has poor connection to the table, and an air gap exists. Therefore, the pulse, when it passes through the sample, will reflect from the back surface, heading back towards the transducer, where it is, in this case, measured by that same transducer. The surface of the sample pushes against the transducer when the wave returns, and the transducer measures that pushing on the surface and converts it into a signal that can be read on the oscilloscope. Now we will set up to detect the pulses using a Tektronix oscilloscope. We demonstrate here the setup of the oscilloscope. What we're going to be doing is effectively looking at the amplitude of the pulses on the y-axis, and x-axis will be time. The time separation between the pulses is used to determine the delay between the pulses, or the transit time for the pulse to go across the sample thickness and come back to the transducer. We have control of vertical cursor bars to make the measurements of the time delay between the pulses. So here we demonstrate the setup of the oscilloscope, and we're going to then start to measure the pulses. What we're measuring is the time between the pulse being transmitted and the pulse being received back, or the time delay between the pulse being reflected back and forth within the sample thickness. We have control over the scaling of the horizontal axis so that we can separate out the pulses in time with sufficient resolution to be able to accurately determine the time delay between the pulses in this video. We'll be able to see all of the different controls that we have for positioning the signal, scaling the signal in both X and Y, capturing the signal, and then being able to make measurements between the pulse that is transmitted and later received from this data. To begin, we're now going to place the transducer in intimate contact with copper step number 1 surface. We're showing here now the initial pulse. Next, we're showing all of the reflected pulses as they come back. So in this case, each pulse goes across the sample and comes back, and then it is reflected back and forth within the thickness. And there's a decaying amplitude. So you can see this nice decay function. Now we're going to scale the x-axis so that we can measure the time delay between the pulses more accurately. Again, here we show you the initial pulse, and when we put the transducer in contact with the surface, you can see all of the reflecting pulses come back. You'll notice here how the gap between the pulses keeps getting longer as we move from one step to the next. As the steps get thicker, the time delay between the pulses increases. So here you can see a very large time gap between them. And as we go to thicker steps of the samples, you can see even larger time gaps between the transmitted pulse and the receiver pulse, and between the pulses as they bounce back and forth through the sample. So we have demonstrated how the thickness of the sample changes the transit time and hence the time difference between the pulses. Now we will demonstrate the specific measurements for the copper sample on the oscilloscope. On the left side of the oscilloscope screen, you can see the pulse that's created by the transducer. Once the transducer is put in contact with the copper step, now you can see the separate reflecting pulses as they go back and forth through the sample. So we can place a cursor at the highest peak of one pulse, and then on another pulse, position the cursor on the same highest peak. Now we can show the time delay between those two peaks. As we move from peak to peak, the time delay should be very close to the same. In this case, it's approximately 700 nanoseconds. Now as we go to step number 2, which is thicker, you can see that the gap between the pulses has increased. So now when you put the vertical position cursors on it to calculate the delay between the two pulses, we zoom in now on the oscilloscope to see that the time is now approximately 1.4 microseconds delay between the pulses. Recall that step number 2 is approximately twice as thick as step number 1. For step number 1, the delay between the pulses was approximately 700 nanoseconds. So for the step that's twice as thick, step number 2, the delay should be approximately twice as long, near 1.4 microseconds. For copper step number 3, again you can see the increased delay or the increased delta between the pulses. Again, we position one vertical cursor on the first pulse and another vertical cursor on the second pulse. And from this we can calculate the delay between the two pulses. That delay will be the same between all the pairs of pulses. So here we're going to between pulse 2 and pulse 3 and see that the delay is 2.38 microseconds. We would have roughly expected the delay to be 3 times the 700 nanoseconds for step 1, and that would have been 2.1 microseconds. But since the thickness isn't exactly 3 times the thickness of step 1, there is some variation. Here, for step number 4, again you can see the increased time delay between the pulses. Again, we position the cursors on the first pulse and the other cursor on the second pulse, finding the same peak location in each pulse. And from that, we can determine the time delay between the two pulses. In this case now for step 4 is 3.2 microseconds. Now we make the last measurement for copper step number 5. You can see when the transducer comes in contact with the step, the reflected pulses begin to appear. And as you adjust the position of the transducer, you can really get a clear indication of the reflected pulses. Here you can see the initial transmitted pulse on the left and the reflected pulses, the two that appear in this time scale. We again position the cursor on the highest peak of each pulse, and now we have a time delay of 4.08 microseconds. These measurements were for the copper stepped block. The wave speed measurements for the other metal samples are included at the end of this video for you to record the values of the transit time for the pulses for each of the 5 steps of each of the material stepped samples. These wave speed measurements are repeated for each of the different metal step samples, as well as for each of the different polymer step samples, and included at the end of this video for later review. So we will end up with 5 wave speed measurements per step sample for the metals, and 3 wave speed measurements for each of the 6 polymer samples. It is important to note here that the time delay between the pulses, the measurement of that time delay becomes a function of how accurately you position the cursors on exactly the same portion of the waveform from one pulse to the next. What we've done here is to pick the same pulse in the sequence in terms of their heights, and use that to determine the equivalent position of the pulse from one pulse to the next. So we're determining the same pulse or peak shape each time so that we can get accurate measurements of the pulse time delays. As you can see, determining what portion of the pulse to put the cursor on is a tricky undertaking and may lead to additional errors. Now to summarize all of the data being collected in these experiments for each of the materials. We are determining the mass of each sample material by using a balance. We're determining the volume of the samples as they have simple geometries by measuring the dimensions of the samples. From those dimensions, we're calculating the volume. And since density is mass per unit volume, we're calculating the density using the mass and volume calculations. These values for density for each material should be compared to values from the literature. Next, we determine the transit time for an ultrasonic pulse to travel from the step surface front face to the back surface of the step sample block, and then reflected from that back surface back to the top surface of the step or front surface. The ultrasonic wave has traveled twice the thickness of the step. From the measurement of the sample thickness for each step, and the time delay between the transmitted pulse and the reflected pulse, or the transit time, we can calculate the wave velocity in meters per second. Now, having calculated the density of the materials and measured the wave speed for the materials, we can use these values to calculate the elastic modulus of the materials using the modified Newton-Laplace equation. The values for the elastic modulus, density, and wave speeds for each material derived from these experiments should be compared to values derived from the literature. In addition, you should assess and report on all the potential sources of error for each measurement and the approximate scale of the measurement errors on the calculated values of the elastic modulus. Lastly, when reporting the elastic modulus values from the literature, make note where available of the technique that was used to make the elastic modulus measurements. In an appendix to your report, suggest whether you think the elastic modulus measurements derived from a tensile test would generally be larger or smaller values than those derived from these wave speed measurements. This is an important point. We'd like you to explain the rationale for why you think the values would be larger or smaller from the measurement from a tensile test compared to the way we measured the modulus values in these experiments. The end. Good luck.